Okay, this video is on molecular shape and molecular polarity, and you should have a handout that looks like this. Okay, so we're going to start with a quick review of what a polar bond is. We did this in our last chapter. So a polar bond results when you have an unequal sharing of electrons. If you want to write add to your definition that it results, of course, from a difference in electronegativity values. And that difference in electronegativity causes the unequal sharing of electrons. In a nonpolar bond, you have an equal sharing or a approximately equal sharing. So your nonpolar bonds are your diatomics, and then your carbon-hydrogen bonds. And your polar bonds are basically anything else where there's a difference in electronegativity. Okay, so all right, so we spent time in the last chapter talking about whether or not a bond was polar. And we're going to broaden our discussion now to whether or not a molecule is polar. And there's a huge difference between the two. And so that's what we're going to be discussing today. One thing we didn't talk about before was something called a dipole, okay, or a dipole moment, which is your second bullet point on your paper, which is defined as a quantitative, which of course means you can put a number to it, okay, a quantitative measurement of the charge imbalance in a bond or in a molecule. So polar molecules and polar bonds have dipoles, okay, so you might want to add that. Polar bonds and polar molecules have dipoles. They're sometimes called dipole moments, and they're sometimes just called dipoles, okay? It's one and the same. But this dipole is a result of this charge imbalance from the differences in electronegativity, okay? The bigger the electronegativity difference, the bigger the dipole. The smaller the electronegativity difference, the smaller the dipole. Okay, so that's what a dipole is, or a dipole moment. Okay, so you have two bullet points that follow on your paper. The first one says, for a molecule that consists of more than two atoms, the dipole moment depends on both the polarities of the individual bonds and the geometry of the molecule. We'll get into that in just a minute. And then your second one says, for each bond in the molecule, we consider the bond dipole. Okay, and that's the charge imbalance between the two atoms. So it's pretty wordy, but let's go into an example, and I think it'll make more sense. All right, so your example is carbon dioxide. All right, so if you would, on your paper, next to your CO2 example, if you would draw a Lewis structure for carbon dioxide, please. And please draw it with the correct geometry according to VSEPR that we have discussed in class. So I'll give you a second to get your CO2 molecule drawn with the correct geometry. All right, you have 16 electrons in carbon dioxide. Carbon, of course, is your central atom. And this Lewis structure you probably have memorized at this point. But this Lewis structure is two double bonds in this case. We spent some time in the past few days talking about VSEPR and molecular geometry. Carbon has two electron domains, the two double bonds. Farthest they can get apart is 180 degrees. So this structure is linear and it's drawn correctly. Okay, so let's discuss the polarity of the carbon-oxygen bond. Okay, so the question is the CO bond polar? Okay, I guess it's a double bond, but it doesn't matter. Is the carbon-oxygen bond polar? And that's an absolute yes. Okay, it's most definitely polar. Oxygen wants the electrons more, it's more electronegative, so that individual bond is in fact polar. Both CO bonds are polar. Okay, so this is a yes. Now, because it's a polar molecule, I should be able to put partial charges on there. Okay, and if you can remember the partial charges, there were two ways to do it. One was with the arrows and one was with the lowercase deltas. For the discussion of molecular polarity, it's best to use the arrows. So here we go. We're going to put the bond dipole, so to speak, just with no number, with an arrow, okay, on the molecule. We're going to point toward the more electronegative atom, and so I have one bond dipole pointing toward this oxygen, and I have the second one pointing toward this oxygen. Okay, so nothing from our discussion so far right there is new. We have only discussed whether or not the carbon-oxygen bond is polar. Now, however, we have to just talk about, is the whole molecule polar? What about the whole CO2? Okay, and this is a different question. Notice I'm no longer talking about the bond. I'm talking about the whole molecule. And so when we think about if this molecule is polar, I'm going to reference my picture here, okay? So the two dipoles, or the two charge imbalances, in this case, are equal in magnitude, size, and they're opposite in direction, okay? It's like there are two arrows pointing opposite ways, pardon my reference there, okay? But they're pointing in different directions. And so because they're pointing in completely different directions, or completely opposite directions, those dipoles cancel. Okay, they cancel because they're opposite. So because the dipoles cancel, leaving no dipole behind, the molecule itself is not polar. Okay, so let's do a little bit of a review here, because this is an interesting situation in that this carbon-oxygen bond is completely polar, and this carbon-oxygen bond is completely polar. But when we talk about the molecule of CO2, the two dipoles cancel out, and the molecule itself is nonpolar, okay? And it's because these dipoles, or the arrows, canceled out. So if you have a case where all your dipoles or all your arrows cancel out, the molecule is nonpolar, but it can still have polar bonds. So this is a kind of a interesting discussion in the difference between bond polarity and molecule polarity, and there's a huge difference, and we have to be sure we're talking about the same thing. Okay, so let me erase this, and we'll go on. Okay, you have a bullet point now that says bond dipoles and dipole moments are vector quantities. For those of you who have taken physics, you should know what a vector is. Vectors have both a magnitude, or a size, and a direction. And dipoles are vector quantities, okay? They have both a size to them, and they have a direction, thus the pointing of our arrow in our CO2 picture. Okay, and only vectors that are completely opposite in size and direction cancel out. So you might want to add that underneath. So only dipoles equal in size and opposite in direction cancel. I'm sure you probably discussed that in physics at some point. So when we're talking about the bond, the overall dipole, okay, or the bond dipole, we have to consider the sum, okay, the vector sum of the individual bond, or I'm sorry, this should be molecule. When we're talking about the overall molecule dipole, we're talking about the vector sum of all the bond dipoles. Okay, do they cancel, yes or no? And this, of course, depends on geometry. That's like your huge takeaway point, that the canceling of these vectors depends on the geometry, and thus why we learned VSEPR before you can learn molecule polarity. Okay, you have to be able to do geometry first before you can do a discussion in molecule polarity, but not bond polarity. So you talked about bond polarity in the last chapter. That's because that has nothing to do with geometry. That is all about electronegativity. But molecule polarity is all about do the vectors cancel based on geometry? Okay, so geometry is your huge idea. Okay, so their next one says consider H2O. So while I'm erasing this, draw a Lewis structure for H2O, and please draw it geometrically correct, okay, based on VSEPR. So in doing these molecule polarity discussions, it's no longer going to help us to draw a Lewis structure that's inaccurate. Okay, we need to draw one that's accurate based on geometry. So if we're going to do H2O, we need to consider the fact that I'll draw it incorrectly first, because this is probably how we all draw it to begin with. Okay, but when I draw it like this, it looks linear. It is not linear because I have 4 electron domains, right? Stemming from a tetrahedral geometry, but 2 are lone pairs, meaning that this thing is bent. It's not linear at all, so we cannot draw it in a linear fashion, or we will be confused. Okay, so there's my water molecule drawn correctly in terms of its geometry. Okay, so let's think about this. Hold on. I gotta build a model real fast. Okay, so here's my there's my H2O. All right, so our discussion is the OH bond polar? It should be a resounding yes, very simple yes. Okay, O is more electronegative, so this OH bond is polar and this OH bond is polar. So I have a vector or a dipole pointing toward the oxygen, remember parallel to the bond, and I have a second one pointing toward the oxygen, again parallel to the bond. Those vectors are equal in size. Why? Because it's an O and an H both times. However, they are not opposite in direction, okay? And we can prove that if we are using our model. So here's my water, and if you think about, and the best way to do this is to think about carrying this vector, okay? This vector in this bond points toward the O, so it points like this. So if I were to carry my vector, my toothpick, through the molecule, it would be pointing this way, okay? So I'm going to take my hydrogen off. And if I were to point my second vector through the molecule to continue it, it would be pointing like this. Notice that those aren't opposite in direction, okay? They don't cancel. This is kind of funky, but they don't cancel at all. If I were to add them together, add those two vectors, remember I've got one pointing like this and one pointing like this. Now they add together to give me a resulting vector that points like this, up toward the oxygen. This molecule has what we call a net dipole. They do not cancel and is thus a polar molecule. So I'm going to draw a big arrow up like this through the oxygen. This is the net dipole. It has polar bonds, and the molecule is polar. Why is the molecule polar? Because the dipoles did not cancel. Okay, very different from CO2 that we just did before. However, I will go back and say, if you drew H2O in a linear fashion, your dipoles would have canceled. So you must account for geometry in the molecule polarity discussion. You must account for geometry. Okay, so there are, well, let me think about this. Okay, there are 5 pictures at the bottom of your paper. If you would, go ahead and draw Lewis structures. They need to be drawn geometrically correct. And think about whether or not these molecules are polar. Not the bonds, but the molecule, okay? Go ahead and pause this video and let, give time to draw these molecules and discuss polarity. And then when you're ready, you can play this video and I will continue discussing them, okay? And then there's more practice on the back. Okay, so if you haven't had a chance to try these, please pause this and work on them now. Otherwise, I'm going to go ahead and give the solutions, give the explanations. Okay, HCl is a pretty easy one. If I draw my Lewis structure, it looks like this. Okay, this molecule consists only of 2 atoms, so it's only going to have one dipole, if anything. Okay, So I have H and Cl. Of course, there's unequal sharing. Dipole points toward the chlorine. It's more electronegative. Question is this molecule polar? Of course it's polar. It's only got one dipole. Can't cancel with anything. Okay, so this one is polar. That was pretty easy. All right, second one, CCl4. A little more complicated. This is a tetrahedral arrangement. I know that because I have 4 chlorines on my... Oh my gosh, I'm sorry. I have 4... Yeah, that was right. I have 4 chlorines on my carbon. Okay, and it takes a tetrahedral arrangement. So notice I am not going to draw it in a cross or a T-shaped, okay, because it is not. So I'm going to do my dot line wedge picture just to try to remind myself that this thing is not planar. Okay, so here it is. And this one's a little bit challenging. So I'm going to build you a model. All right. Okay, so here's my tetrahedral shape. Okay, I know that carbon is my central atom. I should have picked a different color styrofoam, but this is all I brought home. So, sorry. Okay, question is, are the 4 carbon-chlorine bonds polar? Answer is yes. Okay, they are absolutely polar. Chlorine is more electronegative. Chlorine wants the electrons more. So all my dipoles, my individual bond dipoles, will be pointing toward the chlorines, okay, from the carbon to the chlorine. So you can go ahead and draw that on your picture, on your paper. It's just not very helpful in looking at do they cancel or not. Okay, it's actually just quite a mess. But remember, that thing's not planar, so that does a pretty inaccurate job. This is why I have the model, okay? So here we go. This is best thought about in adding 2 together at once. So if I were to add this, it's hard to do, this dipole, okay, pointing this way, together with this dipole pointing that way, I'd get a net dipole that looks kind of like that, okay? Then I'm going to go ahead and remove those so it's not so funky to look at. And then if I were to add, some of you might already see this, if I were to add this dipole, remember again pointing toward the chlorine, and this dipole pointing toward the chlorine together, I would get a net dipole pointing like this. Oop. And look at that. Those 2 net dipoles, one pointing this way and one pointing this way, are totally equal in magnitude and opposite in size, and thus they cancel. But very hard to see without a model. So all the dipoles cancel, meaning this molecule is non-polar. Okay, absolutely non-polar. All right, next 2. Actually, let's see if I can do the next 3. Okay, NH3, BF3, and CH3Cl. Okay, Lewis structures for each. Of course, the Lewis structure for NH3 looks something like this. Again, I'm going to draw it, try to draw it geometrically correct here. Stems from a tetrahedral arrangement. BF3 is an octet rule breaker. Remember, your boron is one who's going to break by going under. This is the best structure based on formal charge. It's flat. Okay, stems from trigonal planar geometry. The thing is planar. And then this one, carbon's your central atom, and you have 3 H's. Oops. And a chlorine attached, okay, stemming from, of course, a tetrahedral arrangement. Okay, so NH3, let me, again, build you a model. Stems from, like we said, tetrahedral. But it's not a tetrahedral because of that lone pair. Okay, so there's your tetrahedral, but this is a lone pair on NH3, so I'm looking at a trigonal pyramid, okay, or trigonal pyramidal geometry. And in this case, N is your more electronegative atom. So all your dipoles are pointing towards your N. So you can add that to your picture if you want. Oh, sorry. Again, doesn't really help us here on paper because the thing's not planar. Okay, when they're not planar, the on-paper picture is not going to help you. You're going to need a model until you get better at this. So pointing toward the nitrogen, again, best to do this in twos. Okay, this one pointing toward and this one pointing toward. Add together to give you something that looks kind of like this, okay? And this one, oops. Okay, so that's gone. And then I have this one left, which is pointing this way, okay? So there are my two net dipoles. Notice they're not opposite in direction. They do not cancel, meaning they would add together to point kind of like this. And so this molecule is in fact polar. Has a net dipole that's pointing kind of up toward the nitrogen, okay? That's the net. BF3 is planar. So this picture is not too bad to look at. BF3 is planar. Okay, looks something like this. Of course, fluorine is your more electronegative atom. All three point toward the fluorines. Polar bonds, absolutely. 3 polar bonds. Question is the molecule polar? Okay, oops. So if we go to think about adding these together, pick 2 an atom. This one and this one add together to give you a dipole that looks like this. Oh, goodness. I lost my other atom. Let me put it back. Whew, okay. And then my other dipole, of course, is going to be pointing toward my fluorine. So there it is. Equal in size, opposite in direction. This molecule is, in fact, nonpolar. Has polar bonds. There they are. But they all cancel. Last one is CH3Cl, stems from a tetrahedral arrangement. The tricky thing here, the takeaway here, is that your carbon-hydrogen bonds are all nonpolar. This whole part of the molecule is nonpolar, okay? There are no dipoles. There's only a dipole that exists between the carbon and the chlorine. Points away from the carbon toward the chlorine. And because there's only one bond dipole, the whole molecule is polar. Okay, and the net dipole is, of course, that dipole because of the fact that the rest of the molecule is nonpolar. Okay, so this is a little bit of a challenging discussion. There is some practice on the back. I don't know, 6 of them, maybe 5 of them. So if you would attempt to state the molecular polarity of those molecules, if you feel like you need to build models, the styrofoam and toothpicks are out for you on the lab table, so you're welcome to do that if that will help to concrete the example. And don't feel too nervous or whatnot, frustrated about this, and we'll do some more of this when I'm back in class with you.